Okay, so I want to take a detour a little bit from our discussion of microstates, macrostates, and how particles distribute their energy to a topic called entropy, because later on we're going to take this quantity called entropy and relate it back to the microstate and the second law of thermodynamics. Okay, the idea of entropy was developed actually during the studies of the efficiency of heat engines. And this all happened around the 17th and 18th century. Those were the times when a lot of these engines were developed that relied on the fact that you are heating liquid water to produce steam, and then the steam is then used to push on something like something mechanical that makes it do work. So the basic idea of these steam engines or these heat engines is that you are able to do mechanical work using steam, okay, that's generated by heating water. And so there were a few scientists that made very important contribution to this field. And this is, in fact, what we later on call thermodynamics, which is the study of interconversion of energy. So the person I want to highlight here is somebody called Sadi Carnot. And what he was doing was he was studying the efficiency of the steam engines. And again, let me just kind of highlight, at least schematically, how these things work. So the idea is you're going to heat water up until it becomes steam, and the steam has a certain temperature, which we call the high temperature. And then that hot steam can then be used to maybe push a turbine or a wheel or something like that that would do mechanical work. So some amount of that heat that's generated from the steam is going to be used to do work, which is the symbol W here. But then what Carnot found is that it's impossible for you to take all of that heat and make it do work. So in other words, this path where you just have the high temperature and then it eventually all gets converted to W to work is not possible. This doesn't work. What ends up happening is there's always some amount of heat that is lost, what we call the colder temperature compartment, and only a certain percentage of this hot steam is able to do work. The efficiency measure is just how much work do you get out of the original quantity of heat that you produce. Okay. Now, the reason why the engines are never 100% efficient is because the heat is invariably lost due to various processes like radiation, just heat just radiating away from the compartment, friction of the equipment that's being used, like the wheel and the other pieces of the machinery and other processes. Okay. So this quantity of heat that we can never recover and that is lost, okay, is what Carnot called wasted heat. So it's just heat that, ideally we want to get that heat and make it do some work, but just due to the way things work, the design of these engines and so on, there's always some quantity of it that is lost. It turns out that another scientist later on called Rudolf Clausius then coined this term entropy, which has the symbol S, to express this quantity of heat that is divided by temperature. Okay, and so this is a new state function. So you remember state function is a function that only depends on the final and initial state for its value. And so this study of this heat engine led to the discovery of this new state function called entropy. And you can calculate the value of entropy, which is again related to sort of the efficiency of these steam engines, by using this expression right here. So the change in entropy, delta S, is just the final value of the entropy minus the initial value of the entropy, because you can do it by taking the integral of this expression. Now, we're not going to do this actual calculation in this class, okay? It's not important for the types of discussions that we're going to have, but this is how we actually will measure values of entropy change. Okay, so this is a quantity that you can actually measure experimentally. Okay, just like you can measure delta H using a calorimetry experiment, you can measure entropy change using an experiment where you change the temperature and measure the amount of heat that is either absorbed or released as a result of it. Okay, well, one of the most important discoveries for entropy is that it turns out that for processes that are reversible, which is actually only true in theoretical sense, the delta S of the universe, the change of entropy of the universe, is zero. Whereas for processes that are irreversible, which is processes where that actually happens in real life, the change in the entropy of the universe is positive. So in other words, what this is saying is that the entropy change of the universe is always either zero or greater than zero. It's never negative, okay? What people found later on is that this is then becomes the second law of thermodynamics, is that every process that is spontaneous, where something on its own goes to a certain final state without any input of energy, that process always has a delta S of the universe greater or equal to 0. Okay, because all the processes that we do in real life are actually irreversible processes. So the only way that could happen is if the change of entropy is positive. Why am I talking about this quantity called entropy that was discovered during the steam engine research, right, or kind of investigation? Well, the reason is because this entropy quantity actually relates to microstates. So we were talking about how microstate is a measure of how particles distribute their energy. Well, a scientist by the name of Ludwig Boltzmann discovered that the entropy that these physicists were measuring, again, based on those ideas from the steam engine, is actually the same as the measure of how many microstates a system has. And Boltzmann famously came up with this equation that allows him to calculate the value of entropy. And this is K, which is a constant, we call the Boltzmann constant, times ln W, where W is the number of microstates, okay? S here is just the absolute end. So in other words, if I have a 10 microstates, for example, if W is equal to 10, then my entropy value is just the Boltzmann constant times ln 10, okay? The Boltzmann constant is given right here. It's just the gas constant divided by Avogadro's number, all right? And so when Boltzmann discovered this relationship, that's when people realized that, this microstates that we're talking about, which again helps explain why certain things look the way they are, why they spontaneously go to that end state, is actually related to this other quantity called entropy that we could measure experimentally. And simply the conclusion that we can draw is that if a system has fewer microstates, which means they have smaller W, they're going to have lower entropy. And a system that has more microstates, which is a larger W, is going to have a higher entropy. Now, we just said earlier from that second law of thermodynamics that every spontaneous process is going to have a delta S of universe that is positive. Right? So that means that if you relate back to the idea of macrostates, so delta S is S final minus S initial. Now, S final is the Boltzmann constant times ln of the final number of microstates minus Boltzmann constant times ln of the initial number of microstates. So if you factor out the Boltzmann constant, all you have is ln of the final number of microstates minus the initial number of microstates. So this delta S, according to the second law, which is based on experiment, has to be positive for spontaneous process, okay? So what that's telling us is that the system will go from a smaller number of microstates to a larger number of microstates spontaneous, okay? So it's not going to go from something that is more microstates to something that's fewer microstates. It's always going to go from fewer microstates to more microstates. And this actually makes a lot of sense because, again, I'm going to go back to this experiment that I showed you earlier, which is trying to figure out how many different ways can I put 6 particles to get a total energy of 9. The idea here is that I could go from this into that because there's only 6 microstates here and there's 180 microstates here. So I could go from a macrostate that looks like this to a macrostate that looks like that, because there's fewer microstates to more microstates. But I cannot go from this to that, okay? And the reason I can't is because the system wouldn't want to do that. There's no benefit for them to do that. Why would they want to go from something that is more likely to something that is less likely? It just doesn't happen in real life. It doesn't happen based on probability. So that's how this concept of entropy change actually helps us understand spontaneous process. So anytime we want to predict if something is spontaneous or not, we can calculate its entropy change, delta S of the universe. If that number is positive, that means that the process is spontaneous. If that number is negative, that means the process is non-spontaneous, okay? So that's the conclusion that we want to take from this section right here. Now, there's one more number that you're going to keep in mind, which is when the delta S of the universe is equal to 0. What happens there? Well, when it's equal to 0, there's no reason for the reaction to go or the process to go one way or the other. So that's what we call equilibrium, okay? And as you might see here, we're going to connect this back to the equilibrium constant later in this chapter. But this is the first time that we start to understand that delta S, which is the change in entropy, is a measure of whether a process is spontaneous or not.